Welcome to Unit 2 in Calculus. Now, this unit is a really big one, and here's why. In Calculus, the whole year, we really only talk about three main topics. We talk about limits, which we've already done. We talk about derivatives, which we're going to introduce today and then do for the next several months. And then we do integrals, which are the opposite of derivatives. Don't worry about them too much right now. So today is where we introduce derivatives. So what I want to start with is to help you understand what the heck is an actual derivative. What does that word even mean? What are we talking about? To understand that, in its essence, derivative is slope. So let's do a quick review up here. Derivative, if I calculate the derivative of something, I'm talking about the slope. So before this point, and we reviewed this last chapter, we talked about there are two types of slope. We have an average slope, or an average rate of change. And to calculate that, we use this equation, which you have seen since junior high. You've seen this equation a lot. That's your slope equation. That means so let's say I have a graph of a parabola. I am taking 2 points. This one is x1, comma, y1. This one is x2, comma, y2. And I am subtracting them to find the average rate of change between those 2 points, or the slope, the rise over run between those 2 points. That's what this slope is. Well, a derivative is your other kind of slope. It's an instantaneous rate of change. So instead of finding slope over an interval, a derivative can find the slope at a single point. So you don't need an interval anymore, it's at a single point. Now let's explain this a little bit more. We have two kinds of lines that we talk about. A secant line is one that you have already known. Secant line is your average rate of change. So let's say right here, that's my function. Secant line is exactly what we were doing before, where I have 2 points on my function, here and here, and I'm going to do y2 minus y1 over x2 minus x1. So your secant line is another word for your average rate of change, or I should say the slope. Let's do this one in green. The slope of a secant line is your average rate of change, aka y2 minus y1 over x2 minus x1. Now I'm going to show you that this equation right here is really just the fancy version of that. y2 minus y1, and I'll show you that this is x2 minus x1. So let's show you that. Looking at this graph right here, what they're saying is that this first point is x, comma, f of x. So there's my x1 and my y1. So right there, f of x is my y1 because of that point right there. Then they're saying at this point, I have x plus some x. That's all this delta x means right here. This is some x. So I'm going to take x and I'm going to add some more x to get to a different point. So if this was 1 and I added some more of 3, then I'd be at 4. That's all that's saying. So the x value here is x plus delta x. So that is my x2. That point is at that x value, x plus delta x. And if I wanted to find y2, I would plug this in to my function. So f of x plus delta x. There's my y2. So right here, it's easy to see I have my y2 minus y1, y2 minus y1. This is x2 minus x1. So x2 right here is my x plus delta x minus my x1 right there is x. And if I simplify that, I can see my x's are going to cancel, and I'm left with delta x. So that's where this part comes from. That delta x is x2 minus x1. We get left with just that delta x. So this whole equation right here is just a very fancy way of saying y2 minus y1 over x2 minus x1, which you have seen forever. That's your secant line. Now, the new one that we're talking about is this tangent line. So the derivative, or the tangent line, let's see, the slope of a tangent line, so the slope of this line right here is your instantaneous rate of change. So the slope of this yellow line would give us the slope at this point. Not over an interval, but at that point. Now, to calculate the slope of this line, I'm going to use my same y2 minus y1 over x2 minus x1 equation. So this is just that fancy slope, but I'm adding this part. This is why we talked about limits last chapter. So what I'm saying is I want to know the slope of the green line as my sum x gets closer and closer to 0. That's what this limit is saying. So this sum x, that change in x, is getting closer and closer to 0. So essentially, we're squeezing that green line closer and closer and closer to the original point. We're changing that delta x to get closer and closer to 0, and then that will give us the slope at that point instead of over the whole interval. So that's what this equation means. That's where it comes from, is I'm taking the limit as the change gets to 0 so that the slope is no longer an interval, it's at that point. That's what a derivative is. That's what this equation means. In the next video, we're going to go about actually applying that equation to calculate derivatives.